Hey everybody, welcome to my video on spent nuclear fuel, societal hazard or resource. In our previous video, we talked about the potential of nuclear energy as a vast source of carbon-free energy that could solve our global warming problem and many others at the same time. However, one of the biggest outstanding issues is what to do with spent nuclear fuel. In the United States alone, we've built up about 76,000 tons of spent fuel over the last 40 years. This is a lot of radioactive material. In fact, only about 2% of the radioactive uranium-235 that's in the initial fuel is actually consumed. So there's a lot of energy left in this so-called spent fuel. And so what should we do with this fuel? There's really two options. And the future of nuclear energy in the US really hinges on this question. One option is to reprocess the fuel. This is what's done in countries like France and India. It's expensive and it's technically complicated, but it has the huge advantage of recovering usable energy, both in the unburned uranium-235 and in the fission products, which are useful for many things. On the other side of the coin is storage. We can also store this spent fuel. This is also expensive, although probably cheaper than reprocessing. But perhaps more worryingly, energy is wasted. We're essentially taking usable nuclear fuel and burying it in the ground. And environmentalists are very worried about long-term leakage risks. Because many of these radioactive elements last for hundreds of thousands or millions of years, it's hard to ensure that we can prevent those radioactive elements from leaking out into groundwater. And a lot of this debate has been revealed and discussed around the proposed Yucca Mountain nuclear waste repository in southern Nevada. And so in this video, we're going to first learn the basics of radioactive decay. Then we're going to learn what is in spent nuclear fuel. We're going to understand when spent fuel might be a health hazard, and then we're going to come back to the Yucca Mountain repository and think about how all these factors control the risk of potentially storing fuel at Yucca Mountain. So let's start with the basics. If you have spent nuclear fuel, where is the radiation and the energy coming from? It's coming from two main sources, alpha and beta decay. And it's worth knowing the difference between these. Alpha occurs when a parent nuclei releases 2 neutrons and 2 protons. So what that means is this alpha particle is spit off, and the residual nuclei has a lower mass. Its mass is now 2 protons and 2 neutrons less. It's literally a different element. So for example, 238 uranium decays into 234 thorium, a totally different element after it releases the alpha particle. On the other hand is beta decay. In beta decay, we essentially convert a neutron into a proton plus an electron. The electron is emitted as a beta particle, but the key idea is that the residual nuclei now has 1 additional proton and 1 less neutron. For example, carbon-14 gets transmuted to nitrogen-14. So it has the same mass, but it's actually a different element. It's now nitrogen instead of carbon. The other key difference between alpha and beta is the energy of decay. Alpha is typically let off about 4 to 10 mega electron volts with each decay, and betas typically only release about half of a mega electron volt. So a single alpha decay releases roughly 10 times more energy, or 10 to 20 times more energy than a beta decay. So considering these two types of decay, how quickly does it happen? The rate of radioactive decay is controlled by the half-life of the parent element. And the half-life is essentially the amount of time required for half of the parent material to decay away. So for example, if we start out with 100% of the parent material, or 1, after a single half-life, we only have half of that left. After a second half-life, we've further cut it in half, and we only have a quarter. Then we split a quarter in half, and we get an eighth, okay? So after each half-life, we remove half of what we started with. So we can see the concentration of the parent declining and the concentration of the daughter increasing. So in this example, the parent might be something like 239 plutonium, and the daughter might be something like 235 uranium. So plutonium is alpha decaying into uranium. So as it's depleted, its daughter uranium actually gets enriched. Okay, so now you know the basics. Let's look at what's actually in spent nuclear fuel. And it's first worth considering, how does fuel become spent, especially if we've only burned 2% of the initial uranium? The way it becomes spent is that each time we fission a uranium, we get a fission product. Actually, we get two fission products because we're splitting it. And these could be a variety of different elements that have masses roughly half of uranium. Things like xenon and cesium. And some of these fission products are stable and have very high neutron absorption cross sections. They are essentially very good at sucking up neutrons. And so as these fission products, for example, xenon-136, build up in the fuel, they start to act like a sponge and sponge up all of the neutrons. As they reduce the neutron density, that ends up killing the chain reaction within the reactors. We simply can't maintain enough neutrons to keep the fission chain reaction going. So fuel becomes spent not because we burned it all, but because we've poisoned it with fission products. So what's in the fuel then? Well, we have two important things in the nuclear fuel, in the spent fuel. One are the fission products themselves, and we just described these. They're generally low mass, but they also have generally short half-lives, which means they decay away quickly, and they generally decay by a single beta decay. So they generally don't release much energy during their decay. The other thing we have are called actinides. These are higher mass elements, like uranium-238 and plutonium-239. These are things that were either in the fuel to begin with, or they were produced by neutron capture in the fuel. These are generally long-lived. They have long half-lives, and they decay slowly. However, they release large amounts of energy because they undergo multiple alpha decays as part of their decay chain. And so let's look closer at how an actinide actually decays. This figure shows the chart of the nuclides, essentially all of the possible radioactive isotopes that exist. We've got number of neutrons on the X and number of protons on the Y, okay? So imagine that we've generated a lot of plutonium-239 in our reactor. So this is an actinide. It has a half-life of about 24,000 years, which is actually not that long, but it's relatively long. This actinide doesn't decay just once. It undergoes a whole decay chain of multiple decays. First, it alpha decays to uranium-235, and it emits 5 mega-electron volts. Then uranium-235 alpha decays to thorium-231, releases another 4 MeV. Thorium-231 then beta decays, releasing a small amount of energy. And then we get another alpha and another beta. And this chain actually continues until we get down to a stable isotope of lead. The key point here is multiple alpha decays occur, and we release a lot of energy from a single actinide isotope of plutonium here, okay? And also, some of these half-lives are very long, millions of years, so this happens relatively slowly. So if we bring together all of this knowledge now, and we look at how much energy or radioactivity is left in spent nuclear fuel, this is what it looks like. And this is interesting for two reasons. One, this is energy that could be harvested to make electricity or to heat stuff. And two, this represents radioactivity that could be harmful to people should it escape over long time scales. So here's what it looks like. Early on in the lifetime of the spent fuel, the fission products are the most actively decaying and they're dumping the most energy. But because they're short-lived, they actually drop off really rapidly after just about 100 or a few hundred years. The radioactivity of the fission products drops way off. In contrast, the actinides in blue, or for example, plutonium specifically in red, they start out with less energy released than the fission products, but because they decay more slowly and they have that long chain, they actually continue to have relatively high energies for long time scales. And they don't drop back below the initial uranium activity until about 100,000 years. So essentially, fission products go away in a couple hundred years, and the actinides go away after a couple 100,000 years. So really, really different time scales dictated by what's actually in this nuclear waste. All right, so let's wrap this video up a bit quickly here. Is spent nuclear fuel a health hazard? We know there's energy in there. We know there's radioactivity going on. Can it hurt us? Well, radioactivity hurts us if it decays within our bodies. And the way it does this is that each decaying particle, an alpha or a beta, essentially travels some distance, and as it does, it damages any molecules that it encounters. So if alpha or beta particles are traveling through your body, they actually damage cellular molecules like DNA and RNA. If these things are damaged by a radioactive particle, they don't reproduce properly and they can cause cancer or cell death. Okay, so this damage is inflicted by the particles at a molecular level. However, alpha and beta particles travel very short distances, okay? The exact range of alpha and beta depends on their energy as well as the density of the material that they're passing through. But typical alphas are stopped in a thickness of as little as a piece of paper, okay? And typical betas are stopped with a thin sheet of aluminum. What that means is you can hold an alpha emitter in your hand and the alpha particle won't even really make it through the thickness of your skin. And the take-home point here is that humans are most vulnerable to radiation if it is ingested or it enters our body. It's very rare that humans would be harmed by external exposure to radiation. Much more threatening is internal exposure, either inhaling the material or ingesting it, where those radioactive particles can get close to your tissues and continue to bombard your tissues with these energetic decay particles, the alpha and the betas. So we know we have to ingest this stuff or breathe it in for it to be dangerous to us. So that shouldn't happen with waste, right? Waste should be contained within containers, and as long as you don't eat it or drink it or breathe it, what's the problem? And this brings us to the issue of nuclear storage. Why isn't it safe to store radioactive waste at a place like Yucca Mountain? So first, let's look at what is Yucca Mountain. Well, it's a mountain in southern Nevada made of a bunch of layers of volcanic rock. It's in a very remote area. And so far, billions of dollars have been spent to develop a centralized repository for nuclear waste. Waste would be stored in a series of underground tunnels that go deep under the mountain along these tunnel shafts and then fan out into a series of tunnels. And the idea is to put casks of nuclear waste within each of these tunnels under the mountain. So that sounds pretty good. Far away from where anyone could eat it or drink it or breathe it, it should be safe under this mountain. Probably the biggest concern and the biggest criticism is that especially these actinides are very, very long-lived. We just saw that their long half-lives mean they can survive for hundreds of thousands of years or even millions of years, okay? So that means we can't predict whether these casks, the storage casks, will be safe over million-year timescales. Could they be corroded by groundwater passing through this mountain? How long will they last? If the casks are corroded by groundwater, and then the radioactive elements are entrained in that groundwater, could they flow down into the water table and then potentially flow towards humans and harm them? This is an interesting question. However, Yucca Mountain is currently in a desert environment. Also, is it even likely that human beings will be on the planet in 10,000 years, let alone 100,000 years? And if we are on the planet, most likely by that point, we will have learned how to use nuclear waste much more efficiently. So in sum, it's really hard to imagine that storage of nuclear waste poses significant long-term threats to our health, at least. So in summary, the first part of this video looked at the basics of radioactive decay, the difference between alpha and beta decay, and also how the half-life of a radioactive element controls its lifetime. We then talked about how nuclear fuel becomes spent as neutron-absorbing fission products build up within the fuel. And it becomes spent when only about 2% of the uranium-235 has been used. And this leaves a lot of energy left in the spent fuel in the form of the ongoing decay of transuranic and fission products. We talked about how the transuranics tend to decay slowly by a sequence of alpha decays and have a lot of energy stored in their decay chain. Fission products tend to decay quickly by single beta decays and thus have relatively less energy in their decay chain. We then took up the question of whether radiation is actually harmful to human health and whether spent nuclear fuel poses a threat. And we showed that it's only really threatening if it enters the body by inhalation or by ingestion. And based on that knowledge, we can infer that Yucca Mountain is a relatively viable option for long-term storage, although there is a long-term risk from groundwater corrosion. Thanks so much for listening. I'll leave you with these concept questions, and we'll see you in class.